Remember these? If you didn't tune into the last video, these are some Arduino Nano microcontrollers that I bought off AliExpress, and they didn't seem to work all that well. Notably, I could get power over the USB-C port, but I couldn't program anything. Nothing would populate in the device manager, and wouldn't show up as a COM port. This effectively means I couldn't program these. Or could I? Now, rewind back a year. My sister says, we're gonna do a no-buy Christmas. And from the start, I knew I wanted to make clocks. And now that we have a whole bunch of microcontrollers lying around, with tons of I/O and a USB port for power, I think this might be the single most expensive part of a clock project. So, in the spirit of no-buy Christmas, we'll see about that later, let's build some clocks. You know, I think this might be my first clock project. Well, functional one anyway. It's kind of a rite of passage for electronics hobbyists to build one. First, where do we begin? Or what's our embedded system architecture here? The heart of our project will be this Arduino Nano, sporting an ATmega 328PB microcontroller. Since it seems like this microcontroller can still run off USB-C power, this USB-C port will be our power input for the entire clock. Next, we need the circuit that keeps the time. This is a DS1302 real-time clock module. It uses a pretty simple serial interface to talk back and forth to the microcontroller, while using a CR2032 coin cell battery to keep the time when it's powered off. It's a great little feature when you have to unplug or move your clock around. We'll also need some buttons to set the time, and finally a display. I've gone with this LTC5851Y. It's got this nice amber yellow color. And that's it. That's all our core components. Now, how do we integrate them all together? Well, that's where this custom PCB comes in. Yeah, I know, no buy Christmas. Well, I guess it still counts. It's like making cookies from scratch. You don't do it at the atomic level. All just ingredients in our little electronic soup. Anyway, if we break this RTC module down to its core components, we're left with a 32.768 kHz crystal, a CR2032 battery holder, the DS1302 real-time clock chip, and its IC socket. Now throw in some pin headers for the Arduino Nano and the display, and that's the whole main board assembly. Now, some of you might be wondering, how does this display with all these pins connect to the main board? Well, easy. Second circuit board. Now, I had to design this circuit board because the 36 pins on this LED module would have been too many for the microcontroller. Basically, there's a pin for every single segment, including the decimal points, and 4 common pins, one for each digit. But what we can do is tie all the segments together, drastically reducing the pin count, and only turning one digit on at a time. This is a pretty common trick known as multiplexing. It's the reason why when you film a 7-segment display, it can be flickery sometimes, and also drastically reduces our pin count from 36 pins down to 12. That's much easier for the microcontroller to handle. Yeah, our little module will go in like that. That's gone. We'll attach our pin header like so. These will go in like this. Our clock crystal goes here. We'll give our microcontroller some pins. And we'll run some wires to our buttons. Now, as you can see, everything looks pretty floppy here and might not line up correctly. To remedy that, I've 3D printed some parts. We got some little brackets that go right here, and a little backplate, which lines up our circuit board and our USB port, and is a place to mount the switches. So without further ado, let's get this assembled. All right, I'll start out with the LED module. See here it says front and back, and the numbers face the bottom. Now I am aware that they do make multiplex 7-segment 4-digit displays. However, this is no buy Christmas. I did not have any multiplex 7-segment 4-digit displays. Or I guess it's really 8-segment, if you count the decimal point. Do y'all enjoy watching me solder? If you do, leave a comment down below. If not, probably speed up these videos a lot faster. There we go. Easy day. Now these little jumper links are gonna be a little strange. Just using some component lead trimmings to bridge those. This LED board was the first board I ordered, and I was a little unsure about what the resistor values would be for these LED modules. After doing a little bit of experimenting, it turned out I didn't even need resistors. I was multiplexing the display so fast. Now I doubt this is good for the LEDs in the long run, but they're hardly bright enough to see to begin with. This is actually the second attempt at this project for me. I wanted to go ahead and use vacuum fluorescent displays, but with their extremely strange voltage requirements and lack of modern day support circuitry, I could not get them to work reliably. All right, and that's our 4 jumper links installed. All right, now let's install the LED module onto the brackets. And there's our little LED module. Now let's work on the main board. Always push down on the components while soldering so that they stay flush. I know these longer pins sticking out the back look a little goofy, but they shouldn't give us any problems. Let's do the CR2032 holder next. Honestly, I'm just gonna solder it right here on the desk. Next is the DS1302 real-time clock. All right, just gonna get that corner pin in, press from the back. Hear that little click. Means it's flush. And I'll do the same for the opposite corner. Perfect. We have the crystal next. And the pin header. Yo, soldering on camera is kind of difficult, you know? Normally I'd be hunched over it like this. Yeah, you really gotta pull yourself away from it. Making sure you're not blocking any shots. And we're done. Well, with most of the main board. All right, now the pin header on the main board should slot right into the LED board. Haha, yes it does. Actually, I'm gonna take this out first, and it should press fit into the back plate here. Yep. You can see the little USB port on the back here. The 3D printer does kind of a sloppy job here, but it gets it done. Now this will go in like that. And we have 4 screw holes in the back. Gonna partially thread them all in first. Get your tongue at the right angle. And yeah, the screw tips are barely poking out. And that in there. This is how I get a screwdriver through the heart, huh? All right. Now let's solder all the pins on the front. And last but not least, we have the buttons. Oh no. I forgot to solder in the 6-pin header here. Yeah, we'll just do this some weird hacky way. It's very important for later. I hate this. I'm doing this the wrong way. See, I should have soldered the header first, because I can't get underneath it. Well, maybe a little, but I wouldn't be able to get to those pins closest to the USB port. Is it electrically valid? Yeah, sure. It's just morally wrong. Come on. There you go. Yeah, that's, disgusting. All right, now for the buttons. All right, these are just 2 momentary buttons. These buttons go in with a 10mm socket. So you just use your teensy tiny channel locks. All right, those should be pretty well secured in there. And finally, as soldering is concerned, I have these 2 resistors and some wire scraps. Basically, the buttons will be tied to ground using these resistors, unless one of these buttons is pushed. Each button has the potential to send 5 volts to its corresponding pin, which overrides the 100K resistor to ground. Here's a schematic. All right. Just got the 5 volts connected to the 2 pins on the switches. We'll install our CR2032 coin cell. And there we have it. That's all the electronics for this clock. Now, let's head over to the bench and do a little programming overview. Okay, here's the code for the clock. There's actually not a whole lot to write home about here. It's pretty bland. Where can I start? Well, first I started here with this RTC by Mancuna in their DS1302 simple example. Yeah, I started out using it, then I found it to be a little too complicated, actually. You see, in order to get data in and out of the DS1302, you have to parse this really weird string. You can see some of the formatting of it right here, and it's pretty clunky. I mean, it works fine, it's just all this string parsing is eating up valuable cycles in my microcontroller. Plus, I guess I'm just kind of an old head in terms of computer architecture, so I want to access the registers directly. So I dug into Macuna's RTC DS1302.h header file, and also the 3-wire library that they're using. And from there, I found the only 2 chunks of code that I really wanted: the ability to get data from the chip, and set data to the chip. And to get data in and out, it's pretty simple. All of the even address values in this column are to write to the registers, and all the odd ones are to read. It's only an off by 1. So if I wanted to know what minute it was, I'd have to read from address 83H, and it would return the minutes. This formatting here, where you represent your 1's place value with 4 bits, and then your 10's place value with another 4 bits, is binary coded decimal. And buried deep within Macuna's code was a really strange way to cast binary coded decimal to a uint 8, and vice versa. I have no idea how this works. It's cursed. But yeah, most of the code is just declaring pins. A lot of it is translating a numeric value, like 1, 2, or 3, to turning on and off different pins in order for a 1, 2, or 3 to display on the 7-segment display. It's essentially a really rudimentary graphics or text library. Some of it is handling button presses. So, fun fact, if you're writing a number like 59 to the clock chip, and you want to increment 1 minute to have it roll over, the chip doesn't do that automatically. Yeah, so if you have bits 6 and 4 set for the 5 and 59, if you're doing what I'm doing, where you're just reading back from the chip, adding a number, and then sending it back to the chip, it's going to write 60 to this H2 register. And yes, it will return 60. So you have to put a little logic in your code that accounts for rollover in the context of time. The last thing I wanted to talk about was my trick to programming these. So first and foremost, I had to go over to Tools, Board, and Boards Manager, and install Minicore. For the record, I have 3.1.1 installed. This adds the Minicore library into the Boards menu, and from there I can select ATmega 328, which is what the Arduino Nano uses. However, what makes this Nano special is that it doesn't use the standard 328P. It uses the 328PB. Now, this just targets the specific chip that the Nano uses, but doesn't address not being able to upload things over USB. But you know what does? This thing. This is a USB ASP version 3. As I recall, you can find them online for about $10 or $15. It plugs into your Arduino like this. And in the Tools menu, you can drop down and select your programmer as USB ASP. And to upload, you just go to Sketch and upload using Programmer. Yours might look different than this because I have verbose mode on for testing purposes. And this part of the uploading process just kind of freezes because I think it's waiting for a serial response from the Arduino. But yeah, even though opening the serial port fails, it uploads successfully. And back to the sunroom. Now that our soldering is done and our clock is programmed, let's move on to really the last part of this video, which is printing, painting, and assembling the case parts. First, I made this case, which is comprised of this shell and this inner bezel. I'll let the me from yesterday explain that, since I needed the night for the glue to dry. And here we are at the bench, where it looks more like an I Spy novel, really. We're gonna take our bezel here, and making sure that the holes on the case are oriented towards the bottom, we'll drop our bezel in. And yeah, it's pretty much press fit. And we'll make sure it's 7 millimeters deep. And there we have it. That seems pretty well aligned. And finally, for this step, I'll apply a little bit of super glue to each of the corners and to the top and bottom. Can be a little hard to see, so a bright light like this desk lamp helps. Here I'll be using this little IC puller to spring the tops and the bottoms of the bezel closer to the insides of the shell. So this just helps to eliminate any gaps in the long runs of the shell or the bezel. Alright, now back to the sunroom. Next, I got a hold of a smoked acrylic sheet. I then used some double-sided tape to stick down a blanking plate that was slightly smaller than the internal diameter of the shell. And after a trip to the screaming metal death trap that's my bandsaw, yeah, I gotta really get that thing fixed. I got the acrylic cut down to roughly the size I wanted. Then, using my bench vise, I clamped down my router and began to route the acrylic. And here it is. A perfect fit. Next, I'm using some rubber gloves here so that the face of the acrylic that faces inside the clock doesn't get too smudged or dirty. Alright, now that it's sitting flush on top of the bezel, I'll use some hot glue to retain it. Probably can't really see what's going on in here. I'm just doing a bead of hot glue. This corner, see a little bead of hot glue around this part, and pushing it towards the front so it doesn't try to separate. And I'll do the same for the other side. Yeah, the reason why I'm using hot glue is, well, I didn't want to use super glue because I was afraid that might fog up the acrylic, and a lot of epoxies are just too messy. Alright, now we'll chuck in our, I don't know, electronic subframe chassis, the actual clock part. There we go. It's a bit of a tight squeeze. Yeah, that's lining up pretty well with the screw holes. I might have designed the tolerances just a little too tight. Yeah, but it's lining up pretty good. Next I'll use some of these M2 screws. I think I'll use the 10 mil. Next I'll be attaching this little pivot joint that I made. This takes 4 of these 2M by 6mm screws. Using the shortest ones I can get so I don't contact the PCB. By the way, these 4 outer ones screw right into the rails that hold all the electronics together. So if the battery ever needs to be replaced, it's just a matter of undoing these 4 screws and popping off the back. And last but not least, we have the base. The base is held together with a nut and a wing bolt. And there we have it, an adorable little clock. And there we have it. Our digital clock is now complete. But you know what's better than a digital clock? Oh. 15 of them. Yeah, that's right. I went ahead and made 14 more. Oh, I think I remember this one. Give me 1 second. This one had a bad trace on its PCB. In short, the microcontroller went bad and I lifted a pad when trying to desolder it, but it's all good now. Originally, I just wanted to do 4 or 5 clocks for my nuclear family, but as time went on, I just started thinking, hey, I'll give gifts to my extended family and some friends. I had ordered 15 boards from JLC PCB and had plenty of spare components, so it was just a matter of having enough spray paint and 3D printer filament. And that being said, why don't I have them all plugged in right now? Well, it's because most of the USB-C cables and power bricks are already packaged up. I ended up getting a whole bunch of cardboard boxes and throwing them on the laser engraver. Then wrapping up the USB-C cables in power bricks and packaging them into the bottom. As for the design of the clock, I knew I wanted to be angular and retro-futuristic, invoking visual design cues from something like Star Trek, Blade Runner, the display from a DEC PDP-1, or even the screen from this Westinghouse terminal. When I asked my buddy Jordan for a naming suggestion, he brought up Johnny.5, in homage to the robot in Short Circuit. And that concludes the clock video. I hope you all have a safe and happy holidays, and I'll see you in the next year. Hello. What's up?
I need copper wire. Real thin stuff. Does Cat 5 have like a whole bunch of real thin copper wire in it?
It can.
It can?
Yeah.
What do you mean it can?
Well, some of it's solid core. I think what we have is solid core, though.
So which of my many spare cables is most likely to have like good thin... You know, like when it has like 6 and they're all like twisted around each other?
I can find you some.
What's that?
That's just, stranded wire.
Yeah, can I have stranded wire, please?
Sure.
And wire strippers.
And wire strippers. Oh, this might be more what you're looking for. The 16 gauge stuff. Has all these little cores inside.
Oh, yes. Oh, yes.
That's the stuff?
That seems good.
All right.
Now, how do I strip it? I love you.
I love you.
And I find you useful.